What do you think about this problem?
That doesn't work.
Why doesn't it work?
Because two right angles add up to 180, and you have to have two more corners to complete polygon.
Okay, so prove it.
Wait, is both A and B marked as right angle?
They're both right angles.
Doesn't that in itself prove that it has more than one right angle? It says at most one.
Well, I'm just saying they're both right angles. I don't know. I want you guys to help me prove that a triangle has at most one right angle.
Like all triangles or just that triangle?
Whenever I have a triangle, if it has a right angle in it, it does not have any other right angles in it. That's what I'm trying to prove. That a triangle has at most one right angle.
If the triangle has 90 degrees, that's where you want to so about the 30 degree.
Okay, so how can we turn that into you're right. How do we turn that into a proof?
Is there a theorem that says that the triangles, the sum of the triangles angles can only add up to 180?
So the triangle sum theorem says that the sum of the three angles of a triangle add up to 180.
Yeah, but you wouldn't.
And isn't there a corollary theorem that says the right triangles, the other two angles can only add up to 180?
Isn't there? So there's a corollary to the triangle sum theorem that says in a right triangle, the sum of the other two angles is 90 degrees. That's right. Very good. Now, how do we prove this? So before you start crying, I hate to stop you first, but we're never going to prove this directly. We're never going to prove just statements, reasons, here's how this works, and it's just not going to work like a proof you've seen before. So let me just go through this, and I see you saying, I hear you saying this, and you're thinking it. So let me just show you how we can do this. Let's just assume for a minute that this triangle has two right angles. Can we do that? Okay, so let's just assume triangle ABC has two right angles. So angle A and angle B are right angles. Therefore, their measures are 90 degrees. You okay with that? So that's what I'm going to start off assuming. Once I assume that, I think then we can say then the measure of angle A is equal to 90 degrees and the measure of angle B is equal to 90 degrees. So let's see, according to the triangle sum theorem, the measure of angle A plus the measure of angle B plus the measure of angle C is how much? You guys already said it. What is it?
180.
180. Okay. So this is the triangle sum theorem. So little substitution here. What's the measure of that angle? According to our assumption, what's the measure of this angle? Hey, what? According to our assumption, what is the measure of angle A?
Oh, I couldn't see.
Okay, 90 degrees. Plus, what's the measure of angle B? Okay, that's better. Plus, the measure of angle C is equal to 180. So that's just substitution.
Wait, how is C 180?
Oh, see.
No, I substituted 90 for the measure of angle A, and I substituted 90 for the measure of angle B, so that I have this. Y'all see what I did? Yeah? Okay. So, if that's the case, I'm gonna have to come down this way now. I have 180 plus the measure of angle C equals 180. Right? I don't even know what the reason. What's the reason for that? We just simplified it. We just added like terms, simplify, add like terms, whatever. And then if I subtract 180 from each side, I get the measure of angle C is equal to 0. So the reason for this would be just the subtraction property. Okay, now that's a problem. What do we know about every measure in a triangle? What do we know about the measure of every angle in a triangle? Can any of them equal 0?
No.
No, they're all greater than 0, aren't they?
Yeah.
If they're not greater than 0, do we have a triangle? We don't have a triangle. So let's think about what we did here. We assumed that there were two angles that were right angles in this triangle. And then from that assumption, we just kind of went through the logical process that led us to a big problem. It led us to where we come up with a statement that goes against a theorem or a definition or a known fact of mathematics, something like that. Okay? So if you can show that this assumption, if you can show your assumption leads to a logical impossibility, then what can we say about our assumption? Can it possibly be true? No, it cannot be true. Okay? So this cannot be true. This is a logical impossibility. Okay? So our assumption led us to a statement that contradicts a known theorem, a definition, a mathematical fact, okay, an impossibility. And if it leads us to an impossibility, then what can we say about our assumption? Can't be true. And if that's not true, then what? Can there be two? So then what? So therefore, okay. So our assumption led us to an impossible statement. So it cannot be true. Therefore, a triangle has at most one right angle. This is called an indirect proof. I didn't prove it directly. There's no way, in fact, I don't think, to prove this directly, that this is the only way it can be. Okay? So indirectly, I want to prove something. How did I begin?
Assume.
I made an assumption, right? Okay, I assumed what I was trying to, if I'm trying to prove something that is not true, or if whatever I'm trying to prove, I just assume the opposite. Okay? I'm trying to prove that there's only one right angle. So I assume the opposite of that. Okay? Temporarily. Just temporarily. Let's just assume there's more than one right angle. Let's see what happens. Okay? And then from that assumption, you just work logically through the consequences of that assumption until you come to what?
Not a true statement.
Yeah, a false statement. A statement that contradicts something that we know for sure is true, like a theorem or a mathematical definition or mathematical fact or something like that. Okay? We come to a statement that is an impossibility. And then you can say, okay, that proves right there that statement's impossible. So my assumption cannot be true. Therefore, the triangle has at most one right angle. Okay? And there are a lot of things out there that we cannot prove directly. In science especially. You can't prove a lot of things directly. But you can show that if you assume that it's true, that it leads to a big problem. And so then you can go back and say, okay, that can't be the way it is. That's how you rule a lot of things out. So if you look on page 336, are you there? There's 3 steps for an indirect proof. How to write an indirect proof, okay, or a proof by contradiction. Step 1, identify the statement you want to prove and assume temporarily that this statement is false by assuming that its opposite is true. Reason logically until you reach a contradiction. Point out that the desired conclusion must be true because the contradiction proves the temporary assumption is false. That's how an indirect proof works. Okay? Let's look over on page 337 from now. Example 2. Relating side lengths and angle measures of a triangle. Let's just follow through. Draw an obtuse scalene triangle, so they've done that. Find the largest angle and the longest side and mark them in red. Find the smallest angle and the shortest side and mark them in blue. What do you notice?
They're opposites.
Yeah. We notice that when we draw this thing, when we draw an obtuse scalene triangle, that the longest side, can I say it this way? The longest side is opposite from the greatest angle. And the shortest side is opposite from the smallest angle. And the medium side, what do you think? What do you think about the medium side?
Opposite.
Opposite the medium angle, can we call it that? Okay. So we know, we can look at a triangle and say, okay, this angle is the greatest angle, so this side is going to be the longest side. Let's think about a right triangle for a minute. What do we always know about the hypotenuse of a right triangle? Yeah, it's opposite the right angle, isn't it? Okay, that's always the case. I showed you this case. How do we know that the hypotenuse is always the longest side? Well, there's a couple ways. But if I draw this in, okay, I'm going to say that is the shortest. From these two parallel lines, that is the shortest distance between those two lines. Okay? And if I draw any other segment in, that segment is going to be longer than our original segment. You agree? Isn't it the hypotenuse of the right triangle? And isn't it opposite from the right angle? Right? Okay. So any other segment that I try to draw is going to be longer than AB if I connect the two parallel lines, isn't it? Because it will be the hypotenuse of the right triangle. It's opposite the right angle. So theorem 6.9 is the triangle longer side theorem. In one side of a triangle, if one side of a triangle is longer than another side, then the angle opposite the longer side is larger than the angle opposite the shorter side. Okay?
Simplified terms, is that what we just did?
Say it again.
In simplified terms, is that just what we just did?
This, yes. Yes, exactly. Okay? And then the triangle larger angle theorem says the larger angle is opposite from the longer side of the triangle. Pretty simple, right? Okay. So they're going to prove this indirectly down on the bottom of page 337. Should we follow through? Okay. So we're given in this triangle that angle A is greater than angle C. Does it look greater than angle C?
Yeah.
That's good. Does BC look longer than AB?
Yeah.
Okay, that's good, because that's what we're trying to prove, that the measure of BC is greater than the measure of AB. Okay, so step one. Assume temporarily that BC is not greater than AB. Now, this is a little bit of a problem. If we say that BC is not greater than AB, what does that mean, not greater? It's, okay, that it is less than or equal to. So you have to keep something in mind. Whenever I compare two things, there's three possibilities. This one's greater, or they're equal. This is called the trichotomy axiom. The trichotomy axiom just basically says there's three ways to compare. Tri. What does tri mean? You guys rode a tricycle, right? Had three wheels, right? So a trichotomy axiom has three parts. Greater than, less than, equal to. If it's not greater than, Easton, you with me, buddy? If it's not greater than, it has to be less than or equal to. And this is a bit of a problem, because if we want to prove it's not greater than, we're going to have to show that it's not less than, and we're going to have to show that it's not equal to. So we're going to have to show both of those lead to a problem, not just one of them. There's two parts that we have to show. This can't be right. This can't be happening. And then we can go from there. So assume temporarily it's not greater. So it follows that it's either less than or equal to. So step two, if it's less than, then the measure of angle A is less than the measure of angle C by the triangle longer side theorem. And if it's equal to, then the measure of angle A is equal to the measure of angle C by the base angles theorem. Remember an isosceles triangle? If two angles have the same measure, they're base angles of an isosceles triangle, aren't they? Okay? So that means the opposite sides are the same length. Both conclusions contradict the given statement. Now, this is something we didn't talk about at the first. You show your assumption leads to an impossibility of a theorem or some known fact or definition, or the given information. If you can show that your assumption contradicts the given information, then it can't be true, can it? Okay? And if we look at the given information, doesn't it literally say that the measure of angle A is greater than the measure of angle C? Okay, so saying that it's less than, that contradicts the given information. And that's something that we forget a lot, is that if we can contradict what's given, then it can't be true. Ashlyn, you with me? You look super excited. Okay. Turn the page. This is the hardest problem you will ever do in your life. They're building a mountain for the set of a play. They get it built, and the base is 32, and one side's 24, and the other side's 26. Which angle is the greatest angle on that mountain? That is correct, angle K. And which one is the smallest angle on that mountain? Angle L. And I guess angle J is the middle angle, isn't it? Isn't that rough? That is some hard stuff right there. Example 4. Which side of that triangle is the smallest? Now this is a little bit tricky because you got 51 and 47. You really probably want to know what angle F is, don't you? What is the measure of angle F? 180 subtract 47 subtract 51 is 82. Right? Which I did not do because it literally did it right there on the paper, right? Okay. So if F is 82 degrees, which side of that triangle is the longest side? Yeah. And which side is the shortest side? You guys are brilliant! Okay. The triangle inequality theorem. The sum of the lengths of any two sides of a triangle are greater than the length of the third side. Did you guys know that? Did you know that in a triangle... Ooh, I hope I'm not out of paper. That in a triangle, the sum of any two sides is greater than the length of the third side. So if this one's 5 and this one's 8, this one can't be anything. Like you can't just choose some random number, Mason. Choose a random number. 9. Can that thing be 9?
Yeah.
Yeah. Can it be 19?
No.
Why not?
Because 8 plus 5 is 14, and if a 14 units long segment wouldn't even be able to touch both sides of the 19 long.
Yeah. Here. Let's. I want to make one that'll actually fit on my ruler here. Let's do 3, 5, and 9. What do you think about that one? That gonna work?
No, it has to be less.
Not according to the triangle inequality theorem. But let's take a look at it here for a second. Let's make one side of the triangle, let's literally make it 9 centimeters long. Okay? And let's make one side 3 centimeters long. And the other side 5 centimeters long. So here's the one that's 3, and here's the one that's 5. See a problem?
Yeah.
It's not going to work, is it? They're not going to come together. It's not going to form a triangle. What would happen if this were an 8?
Then it still wouldn't work because it just formed a straight.
By the time they actually came down and touched, what would happen?
It would be a straight line.
Yeah, it would be a straight line. Maybe I should have left that a 9 here. Let's leave that a 9. Make this one a 4. So we would come over here and you guys, you can see it, can't you? You can just see that they're not going to come together until they're actually laying flat. It's not going to make a triangle, is it? So the sum of any two sides of a triangle has to be greater than that third side. Okay? So had a lot of stuff today, haven't we? Okay, first of all, when you're given a problem like this, don't assume that 14 is the longest side just because it looks like it's the longest side. Okay? You have to think about, all right, the sum of any two is greater than the third one. So you have to make 3 different inequalities. You have to say, well, what does x plus 14 have to be? Frisian, what does x plus 14 have to be? I'll give you a hint. It's not going to equal anything. It's going to be greater than something. Yep, it's going to be greater than 9. Carly, what is x plus 9 going to be? Greater than 14. Kimball, what does 14 plus 9 have to be? Keep going. So these two added together is less than 9. These two added together is less than 14. These two added together has to be less than. There you go. You went one more step, okay? Which is fine. So what you're going to find with these three inequalities is 2 of them make sense. 1 of them just doesn't make sense. Let's look at it for a minute. If I subtract 14 from both sides, that says x is less than what, or is greater than what? What does it say?
-5.
-5. Well, isn't one side of the triangle going to be greater than -5? What triangle in the world can you pick out a side and say it's not going to be greater than -5? Is that ever going to be a thing that we're worried about? No. Okay, and so one of these is always going to be like that, where you're just like, okay, I knew that before I got in Mr. Collard's class, right? I hope. Okay, this one says x is greater than what? 5. This one says x is less than 23, which is what Kimball said before. Okay, so what you have is, you have this AND compound inequality. X is greater than 5 and x is, so it gives us a range of numbers that x can be. Okay? Now, we don't want to write it this way. At least we're going to put x is less than 23, like that. I'm not going to put 23 is greater than x. That's kind of hard to understand. But I think we better write it as a compound inequality. Little number on the left, big number on the right, just like they're on the number line. X in the middle. What do the 2 alligators do? They eat the big number, of course. They're alligators. They both want to eat the big number. And this is what an AND compound inequality looks like. And here's how we read it. Ready? X is greater than 5 and less than 23. And if you want to say x is less than 23, you can say that again. Okay? So that's how we read it. Here, you need to do one. Do this one. Come up with a compound inequality for me.